All right, here we are again. So what we're doing today, first we're going to go over the sample midterm number 2. Oh, here we go. Oh, okay, that's good. Thanks for letting me know. Okay. Anyway, so yes, we have the second sample midterm to look at. Now, this one is just based on chapter 8. So it's not quite as long as what we've done in the past. So when this is done, I'll post the solutions on Moodle as well as the actual second midterm. And as usual, you can have about a week or so to do it. Let's see if we can aim for next Monday night at midnight. And that should be plenty of time because, like I said, this is not nearly as long as the first midterm. I think if I remember correctly, there's only 10 or 12 questions on it instead of like whatever the other one was. That was a lot of questions. But so anyway, here's what we'll be doing. And then when we're done with this will not take up the whole class. We'll go back and revisit chapter 11, which we're not done with. We actually are getting close to the end of it, but we're not completely done. We still have one more very important topic to cover. And if you remember, we had 3 rules that we wanted to define, and it's the last one that we want to do today, or at least get started with it. The so-called multiplication rule is still to come. And it's a very complicated rule. So we're going to need to build up to it very, very slowly and introduce several important new concepts before we actually dive right into it. But that's coming later. Right now, let's do this problem set now. So I've already started to work on the answers, as you can see. So why don't we go through them and let's make sure that you've gotten the same answers that I did. So in the beginning, for example, what exactly is an annuity? Now, technically, an annuity should only refer to an annual stream of cash flows or streams of annual cash flows. But in practice, we tend to use it for any situation where we have regularly occurring payments that are all of the same size. Okay, so we use the example car payments could be thought of as a type of annuity. We can think of that as a monthly annuity because they're all the same amount. I'm thinking next Monday at midnight. In other words, the 19th. That's you won't need a week, but you can have it anyway. But let's say a week should take care of it. That way you can do it over the weekend if you want to. But yeah, it won't take nearly as long as the last one. I'll just put it up as soon as we're done here, because then we'll be completely done with our reviewing. And so you'll have the problem set from chapter 8 as well as this sample midterm to study from. Or review it while you're doing your actual test. So, and chapter 8 itself, of course. So you should be fine. All right, now. So anyways, as I was saying, an annuity is a repeated stream of equal payments that take place in most cases annually, but they can also take place monthly or weekly, as the case may be. So the key detail is that it is a periodic stream of equal payments. The most important detail is that each payment is the same. So with a car loan, a typical car loan, all the payments are equal to each other and they take place every month. So we can think of that as a monthly annuity. Technically, that's not the way it should work, but that's the way we tend to do it in practice. It's technically, the word annuity means annual, but we often use it to represent monthly cash flows as well as other types, as long as they're equal payments. All right, enough of that. Now, simple interest. You'll recall this is the interest that's paid only on the principal. That's it. Okay, and because of that, it is not going to be affected by the compounding frequency. All right, the compounding frequency does not determine the amount of simple interest that we earn. That is only for what's coming next, which is compound interest. All right, and so you can see in the next row, part C, what is compound interest? Unlike simple interest, which is paid only on the principal of a loan or deposit, the compound interest is interest on interest. In other words, as you accumulate interest in your account, then you earn more interest on that interest, and that is referred to as compound interest. Altogether, of course, the total interest that you will consist of both in most cases. But simple interest, again, remember, is based on principal, the amount you've borrowed or lent, and compound interest is interest on previously earned or paid interest. All right, now, here we go, APR. And by the way, and just in case you've forgotten, let me sneak this in here. APR, which stands for annual percentage rate. I guess I'll put it down here. Just in case you started to forget, this is annual percentage rate. This only measures the interest that you're earning on your principal. In other words, it is the amount that you're earning on this. It is the simple interest that you're earning based entirely on your principal. And I did mention, I think once before, that when you go to a bank, they typically have signs showing you how much interest they're paying or charging for various products. And they normally they'll show you both of these numbers, APR and EAR. The APR is the first number, the smaller one. It represents simple interest only. And then, of course, the EAR, which is actually effective annual rate, is both the simple and compound interest. So that's why the EAR is the more realistic measure of how much you're paying or how much you're earning, depending whether you're borrowing or lending, because it incorporates both the simple and the compound interest. And so in the bank, when they show you both numbers, you'll know right away which is which, because the EAR is typically higher than the APR, but it is also the more meaningful of the two. Now, I'm sure if you have a credit card, you've noticed this yourselves. When you buy or you get a credit card, it comes with a little packet of information. It's a legal document with, it's a very densely written legal document, but somewhere in there, they have to tell you the APR that they're charging you, as well as the corresponding EAR, so that you know how much it costs you to borrow money with your credit card. So just remember always, EAR is compound and simple interest. APR is simple only. Now, here's an interesting question. For an investor who keeps funds in a 5-year CD, which measure is providing the true rate of return, the APR or the EAR? Well, the APR gives us useful information, but it does not take into account the compounding frequency of our deposit. So it's really the EAR that tells us what we need to know, which is how much interest we're earning every year, including both simple and compound interest. Now, many banks show both APR and EAR, but the ones who only show a single number, that would typically be the EAR, because that's the amount that really matters. So if you only see one number, it's probably the EAR. All right. Now, in one very unusual case, APR exactly equals EAR. What does it take for that to happen? Well, it turns out that with annual compounding, or in other words, n equals 1, these two numbers will actually equal each other. Because remember, the EAR reflects the compound interest. If the interest is only paid once a year, then the two will be exactly the same. So then, as the compounding frequency increases, in other words, as n gets larger, what happens to the simple interest paid on a deposit? Well, this is kind of a trick question, because the answer is the simple interest is not affected by the compounding frequency. How do you know? Because remember, the simple interest formula is, I'll just throw that in here now. The simple interest formula is I equals PRT. Since the formula does not contain the compounding frequency n, it cannot be affected by n, or the compounding frequency. Okay, so in other words, it's the same no matter what the compounding frequency is. And you can tell why just by looking at this formula. If the formula does not contain an n, then clearly n has no influence on the value of I, the simple interest. Okay, so, but just be aware that the simple interest, since it's based on principal, the principal itself is not affected by the compounding frequency. So therefore, that's not going to happen. Now, on the other hand, what about the compound interest? Is compounding interest, as the frequency increases, and we've seen many examples of this, what happens to the compound interest? It keeps increasing. Okay, so we have seen this in our examples. The higher is n, the more is the compound interest that we earn. All right, so as the borrower, as the lender, the person who puts money in the bank, you want the compounding frequency to be as high as possible. If you're the borrower, you want the opposite. You want a very small number of compounding periods. Now, of course, everybody gets charged the same anyway. Normally, in most cases, compounding frequency is 365 days a year, but for certain products, that might not be the same case. So most of the time we're seeing daily compounding, whether you're borrowing or lending, but there are other situations where it might be different. Now, how about this one? This is a straight ahead math question. For a deposit of $10,000, which means that's our principal, with a rate of 5% for 2 years, how much simple interest is paid? So let me just quickly sneak in here. The identity of these variables. P is obviously then $10,000. R, the rate is 5%, and T is 2 years. So once we have that information, we go back to our familiar simple interest formula. And when you plug those in, you'll get $1,000. Okay. Now, how about this one? For how long would a sum of $5,000 need to be deposited in order to earn $1,000 worth of simple interest when the rate is 5%? Now, you notice they're only asking about simple interest, but what's missing from here is time. They're asking us to figure out the time frame that's needed to earn $1,000 worth of simple interest based on a principal of 5,000 and a rate of 5%. So we're solving for T. And if you recall, from the original simple interest formula, we can easily rearrange it algebraically and solve for T, as you can see right here. And you'll end up with T equals I over PR. Now, here's where we have to be careful. When you plug in these numbers, in fact, you know what I'm going to do? I'm going to add another step here. This is actually 1,000 divided by, so when you multiply 5,000 by 0.05, you're getting $250. So what you can do is one of two things. You can simplify the denominator and then just calculate that ratio. Or if you want to do this directly, just make sure you use parentheses for the denominator. Don't forget about the parentheses. If you don't have the parentheses, you'll get a number that's way off. All right, so that's the only tricky part. Or if you simplify it first, you don't even have to worry about the parentheses. Very good. All right, so hopefully by now, after all this calculator practice, that you are getting very comfortable with the calculators, and you therefore should not make these kinds of mistakes, but still you have to be careful. All right, that's the bottom line. You have to be careful. Very good. Now we're moving on to the word problems. Well, actually, no, they're not word problems. They're algebraic problems. The word problems come at the end. Okay, so first things first, in number 2, we're being asked to calculate the future value of a sum under the following 4 assumptions. All right, what are those assumptions? Well, here's this chart, which, now it doesn't fit anymore. Let me fix that little problem. There we go. Oh, no. Okay, so we've got a chart here with 4 different setups. In the first column, we have principal. We have the rate of interest, which is listed as a percentage, which you will convert to a decimal. We have the compounding frequencies. And then finally, we have the actual time measured in years. And because we have compounding frequencies that could be more than once a year, this is the formula that we'll use. Okay, so remember, this is how we calculate the future value of a sum when there might be compound interest taking place. Okay, we had another formula for simple interest only. This is the one that it has to be used if there's at least a possibility of earning compound interest. So if you recall, let me just quickly remind you what these terms mean. A is the future value. P is the principal. R is the rate of interest, which is actually the APR, by the way, and N is the compounding frequency. And then finally, T is the time in years. So this is our formula for calculating future value when there's potentially at least compound interest involved. All right, and you can actually use this in any case. I mean, even if it's simple interest only, you can still use this formula, but N will be equal to 1. Anyway, so for the first case, let's see, I'm going to split the screen so that we can see the table at all times. Okay, so for part A, we'll just note that the principal is 1,000, the rate is 5%, the frequency is 2, and the time is also 2. So what I've done is I've substituted these numbers into the formula, but I also went ahead and simplified it because that's the best way to avoid mistakes. Now, once you reach this point, you've got a couple of options with the calculator. One possibility is that you can compute 1.025 to the 4th first. And that turns out to be equal to 1.10381.3, let's say, and then multiply by 1,000, which gives a future value of and you can just round it to dollars and cents. That's one possibility. Do this simplification. In other words, take the 1.025, multiply, or raise it to the 4th power. So you have 1103.81. Now, another option is just go straight left to right. But if you're going to do it that way on your calculator, then you have to be careful with the parentheses. All right, so let's see what that would look like. You would have 1,000 times, open parentheses, 1.025 raised to the 4th power And that should do it. Let me just double check on my calculator. All right. I'm going to get mine out real fast here. And 1,000 times, open parentheses, 1.025 raised to the fourth power, close parentheses equals, yeah, that did it. Okay. 11,083.81. All right, so you just have to be careful with it. The most important detail is to make sure that within the parentheses, you take the 1.025 and raise it to the fourth power, and then make sure you close the parentheses before you hit the equal button. If you did that correctly, you'll have the right answer. You can decide which one you want to do. It's up to you, as long as it works, of course. All right, now for part B. So in part B, the principal is $5,000. The rate of interest is 6%. The compounding is quarterly, or 4 times a year. T is 5 years. So what I've done here is I've simply plugged in the numbers, of course. And what you'll notice is that when you simplify it in the parentheses, you've got 1.015 raised to the 20th power. And then using either technique with your calculator, you should come up with 6734.28 rounded to dollars and cents. Okay. Very good. Now for part C, you can see that the principal is $2,000. The rate of interest is 9%. And again, I'll remind you that when you use percentages, make sure you convert them into decimals before you use them in a formula. The compounding frequency is monthly, or 12 times a year, and this is a 7-year investment. So therefore, when you plug in these numbers, here's what you'll get. $2,000 times 1 plus 0.09 over 12 to the 12 times 7 power is 2,000. Now 0.09 over 12 is 0.75%, which is 0.0075. The exponent is 84. So either way, whether you multiply straight across from left to right and use parentheses, or whether you do the 1.0075 to the 84th first, you'll still end up at 3746.40 rounded to dollars and cents. All right, and then there's one more. We have a principal of $4,000. The rate of interest is 11%. Now, this one's a little tricky because the compounding frequency is daily. So we have to be a little careful with all our decimals. And then finally, T is 10 years. Well, so here's what I had to do. So when you plug in the numbers, you can see when the interest rate is really, really small. So you need to keep more digits of accuracy than you normally would. Otherwise, you'll wind up with some major rounding problems. So I ended up with keeping, 1, 2, 3, 4, 8 of them. That's fine. With such a small number, that's pretty important. So you've got 4,000 times this number, 1.00300137. the exponent is 3650 because it's 10 years of daily compounding. So over that period, you'll have 3,650 compounding periods. You might think you're going to wind up with $1 million, but no, it's not growing that quickly. But you'll see that at the end, you'll end up with $12,014.67 when rounded to dollars and cents. Now, if you're getting something slightly off, like off by a penny or two, that's fine. You're probably just rounding it slightly differently. But if you're getting it off by more than that, you want to go back and double check your results. Okay, so just be aware that, these only have to be accurate within dollars and cents, but you still have to be careful with all these decimals. Now in the next section, now I can get rid of this split for the time being. Oh yeah, look what we have to do now. Now in the next set of questions, we're looking at future values of annuities. And you can tell right away by looking at this chart, because instead of having principal, principal, we have instead the repeated payment or periodic payment. So that means that in these cases, the payments occur more than once. And that changes everything with our formula. There's a completely different formula that we need to use, which is just meant for future values of annuities. So the principal P is replaced by periodic payment R, or R could be thought of as repeated payment. The rest of it is exactly the same. All right, so, oh man, so this is the formula that we'll be using. And you recognize it right away because there's this capital R here, which tells me that this is a repeated payment. And therefore, this is the future value of an annuity, which I'll just remind you right here. The only thing that's different this time is capital R is the repeated payment. The rest of the variables are exactly the same. For example, I guess I could put them back in. Lowercase r is the interest rate, n is the compounding frequency, and t is the time in years. Okay. Okay, so just a quick reminder, and so we'll be using this formula for the next 4 questions. And so let me just split the screen again so we can see the table. All right, so for number 1, we have a periodic payment capital R of 500. The rate is 4%. The compounding frequency semi-annual means twice a year. And then finally, T is 2 years. Now, here, the plugging in itself is a bit of a challenge because there's so many moving pieces here. But you can reduce this thing a little bit in complexity. And so you might want to think about doing that because this could really become quite a mess if you're not careful. So if you notice what I've done here, this piece in the brackets is 1.02 raised to the 4th minus 1, which you can see over here is approximately equal to 0.082432. And that, what is that, 6 digits? That is probably enough for these problems because, again, we're rounding to dollars and cents. Now, once that's been finished, you can now just simply multiply the 500 by what's in the brackets. Don't forget to hit the equal sign and then divide by 0.02. So yes, you do have to, while you're able to simplify it a little, you still have to be careful. This would be 5,000 times, oh my God. No, we're not going to look at that. But I'm going to toss it aside just for later reference. Okay, so 0.08242 equals, divided by 0.02 equals. Make sure you have all those steps, otherwise you're not going to get the right answer. All right, I'm going to go to my calculator right now and confirm that. 5,000 times 0.082432 equals, divided by 0.02 equals, let's see, what did I do? I think I made a typo here. 5,000 times 0.82432 equals, divided by 0.02. Wait a minute. Is that the right answer? I think there might be a typo in here somewhere. 1.02 to the fourth. Okay, no, I made a typo. It's fine. All right, very good. All right, so that would be the way you can come up with this number. It might be the best strategy. You don't have to, but if you try to do this one from left to right, you'll need a lot of parentheses, and we don't necessarily want to see that, because the more parentheses there are, the easier it is to make a mistake. All right, now for this one, what do we have? So we're told that R is 1,000, the periodic payment is 1,000, the interest rate is 6%, it's semi-annual compounding, and it's a 5-year investment. So we're going to plug in these numbers. We'll reduce it to 1.03. In the brackets, we have 1.03 to the 10th minus 1, which is approximately equal to 0.343916. And so when you get through multiplying everything out, you should get approximately 11,463.88.
I have a question.
Yes, go ahead.
So, what happened to the -1? Because I thought we were supposed to subtract that.
You are. If you type into your calculator 1.03 to the 10th, you'll get 1.343916, and then you subtract the 1, and that reduces it to 0.343916. In other words, this is the result of doing both. You take your 1.03 to the 10th, you'll get 1.343916, and then when you subtract 1, you'll get 343,916. Okay, so that's why it has this value. Otherwise, anytime you take 1 plus some constant and raise it to a power, you'll get a number greater than 1. So after you subtract 1, that's what leaves us with this number. All right. So does everyone get that number, I hope? Yeah, you can see these are definitely more work than the present value of the sum, future value of the sum. These are future values of an annuity. And of course, the numbers are much larger too, because the payments are being repeated multiple times. All right, so I think we're ready for part C. Here we go. So we're told here that the principal is 2,000, not the principal, the repeated payment is 2,000. Interest rate is 8%. It's quarterly compounding. And finally, T equals 8 years. So when we plug in the numbers, you'll see that in the parentheses or the brackets here, we've got 1.02 to the 32nd power minus 1. And you can see over here on the right-hand side, this is equal to about 0.884541. So if you carry on and do the multiplication there, you should get approximately 88,454.06, depending on how much you round it right here. Okay, if you round it too much here, you'll get a number which is off a bit. So try to keep at least 6 digits here. Otherwise, you couldn't get too much rounding going on. Normally, within a penny is fine, but you want to keep it as close as you can. All right. Wow. So there's just one more of these. These are definitely the most complicated of them all. When you're done with these, everything else will seem like a breeze by comparison. Easy. Okay. So for D, this time we have a $1,000 repeated payment. 12% is the rate of interest. Quarterly payments are made. This is 4 and equals 4. And it's a 10-year investment. All right. So first things first, let's plug in the numbers. And then we can do some simplification. So you plug in the numbers. And this should reduce to, in the brackets, 1.03 to the 40th power minus 1. What that turns out to be approximately 2.262038. And of course, once you've done all the multiplication, you should wind up with about $75,401.26. Okay, so they're all done the same way. It's just a question of being careful. And of course, also making sure you use the right formula. Okay, you have to be aware and pay attention to the fact that this says periodic payment. It also says the words annuity. So make sure you're using the right formula. If you get that wrong, of course, the whole thing is wrong. You can't get the right answer if you're not using the right formula. All right, now here we go. Here comes a problem set that will be a little bit simpler. The formulas that we need here are not nearly as messy as what we've just gotten through doing. That's good news, isn't it? Yes. So let's see what this is all about. What we're trying to do now is calculate EARs. Given these rates, this rate is an APR, by the way. That R that we see in all of our formulas is an APR. The EAR basically takes that and extends it to include compound interest. The formula is very simple compared to what we've just been doing. We have E, which is the EAR, little r is APR, and N is the compounding frequency. And that's all that we need to know. If you notice, there's no T here because this is just a simple annual percentage. The number of years in which you leave the money in the bank doesn't affect the EAR. It only affects the future value. So this is all we need to know. So we're going to do the same thing we did earlier. We'll plug in the numbers. We may need to simplify it a little, but then when we're done, we'll end up with the equivalent EAR for each of these APRs. And a helpful hint, unless we have annual compounding, each EAR should be greater than the APR that you see in this table. If not, something went wrong. Like, let's look at this one, for example. First, let me split the screen because I want to be able to see what I'm doing. Yeah, all right, hold on. Whoops. Okay, so part A, we have a 4% APR with semi-annual compounding. And So therefore, when you plug in the numbers, if you notice, this reduces very nicely to 1.02 squared minus 1. And that you should be able to do without too much difficulty in the calculator. All you have to do, I don't think you even need equals in this case, or only at the end, 1.02 x to the y 2. Now, I think, let me just double check that. Maybe not. Oh no, you do need the equal. Then you subtract the 1 minus 1 equals, all right. And that leaves you with 0.0404, which of course means the same thing as 4.04%. It's the same thing. Very nice. All right. Now for part B, what do we do for that one? With part B, we have a 6% rate of interest, which is compounded semi-annually again. So it'll be a similar type problem. Plug in the numbers. This time we've got 1.03 squared minus 1, which ends up giving us 0.0609 or 6.09%. Okay. So you could, yes, like I said before, these are all pretty straightforward. In the third case, you've got an 8% rate of interest with quarterly compounding, which of course means 4 times a year. And so now all you have to do is plug in those numbers. And this will reduce to 1.02 to the 4th power minus 1, which is approximately 8.24%. Okay, and then in part D, the rate jumps all the way up to 12%, and we still have quarterly compounding. How does that work? Well, let's find out. This time, 0.12 divided by 4 is 3%. So you've actually got 1.03 to the 4th minus 1, which leaves us with 0.1255 or 12.55%. That is our EAR. Beautiful. Now, all that's left to be done here is a few fairly straightforward word problems, which you recognize from previous problem sets. So the question with these is just trying to identify what kind of problem they are. Then, of course, using the correct formula. But the challenge with word problems is to figure out exactly what you're supposed to be doing. But these are very straightforward, so you shouldn't have any trouble with them. Okay, let's see, where are we? Oh, here we go. Number 5. So here's William, who's borrowing $10,000 to finance his senior year at SUNY Purchase. Where he's majoring in the history of underwater filmmaking. Well, that sounds intriguing. The loan is repaid in 5 years, and he's paying $2,500 in simple interest. If that's the case, what rate of interest is he being charged by the bank? So you recognize this as a simple interest problem. Okay, in other words, I equals PRT. One of those problems, yes. So what do we know? We know that the principal is $10,000. We know that the time is 5 years. It's a 5-year loan. And we know that he'll ultimately end up paying $2,500 in simple interest. What does he need to know are, so you might recall that with these types of problems, we can rearrange the formula algebraically to solve for whatever we need. So here, that happens to be R, or I over PT. Now, here's where we've got to be careful again. If you're going to write it out directly like this, substitute in 2,500 for I, P is $10,000, and the time is 5. You can do one of two things. You can use parentheses in the denominator, or else you can simplify the denominator first, and then you can easily calculate 2,500 over 50,000. That turns out to be 0.05, which is the same thing as 5%. If you choose to use the calculator directly without the simplification, you would have to hit divided by open parens 10,000 times 5. I believe that should do it. Let me just confirm that. Yep, that did it. 0.05. Okay, so the final answer is 5%. He would have borrowed the money at a rate of 5% per year. All right, what's next? Number 6. Now, in this case, we have somebody who's borrowing money as well, except that this time we're told that Cynthia is borrowing a sum of money for 5 years, that's T equals 5, to finance the purchase of a new car. The interest rate is 5%, and she'll ultimately pay $5,200 in simple interest. How much did she borrow? So this time they're asking us to solve for the principal. So if we go back to our simple interest formula, we have I equals PRT, but then algebraically, P equals I over RT. So in the numerator, we have 5,200. In the denominator, we have 0.05 times 0.5. So again, using this, you can use this approach, or else you can simplify the denominator, and you'll see that you have 5,200 over 0.25, which gives me an answer of 20,800. So that means Cynthia has borrowed $20,800 to buy the car. Okay. Well, that was pretty straightforward. One more, though. Okay, now here we have Ralph, who's deciding to start up a new business selling smoothies. But the thing is, he wants to sell flavors that are not available elsewhere. He discovers that some of his best sellers are peanut butter and jelly smoothies, avocado and anchovy smoothies, and horseradish and honey smoothies. Okay, well, there's no accounting for taste, is there? If they sell, they sell. He's going to sell these because people want them, apparently. So imagine yourself running across to get to your class, and all of a sudden there's a smoothie stand there, and you can gulp down a horseradish and honey smoothie on the way into class. That would be nice, wouldn't it? Anyway, so Ralph borrowed $100,000 to start this business at a rate of 7%. And by the time he's done, he'll end up paying $35,000 in simple interest on the loan. Therefore, how long did he borrow the money for? So this time we're solving for T, the time. We also know that the principal is 100,000, the rate is 7%, and the interest, or simple interest, I should say, is 35,000. So what do we do? Oh, that's right. We can take our original simple interest equation and rearrange it and solve for T. which means I over PR. So we'll take our $35,000 in simple interest and divide by 100,000 multiplied by 7%. Now, if you simplify this, you can see very quickly and easily, you've got 35,000 divided by 7,000, which of course means 5 years. So the money was borrowed for 5 years. And of course, the other option is to just go to your calculator and do one of these. And that'll give you a 5. All right, so the key to the whole thing, as always, is be careful with those parentheses. And equals 2 while you're at it. Yes. All right, well, that's it. We're done with this. So now I'll post it, like I said, and you can, I'll have the actual exam up in a bit, and you can work on it for about a week and hand it in, and then you'll be all set with midterm number 2. And then, of course, that means that all that's left is the final exam, which is only on chapters 11 and 12, by the way. It is not comprehensive. So you can breathe a sigh of relief if you were worried about that. It's just the last 2 chapters. All right. So let's get back to chapter 11. We saved the most complicated rule for last. Okay, so I mentioned a little while ago, we introduced or mentioned last time that there are actually 3 rules of probability that we need to know. These are designed to help us understand what's happening in very complex situations. We've already seen the addition rule, for example. Remember, this is our addition rule, and there's a simpler version of this that's reserved for cases when A and B are mutually exclusive, where we do not have to bother subtracting this intersection because it has a probability of 0. All right, we also introduced the complement rule, but before we did that, we had to explain what it means for 2 events to be complements. You might remember that if A union B is the entire sample space and A intersect B is the empty set, then we say that A and B are complements of each other, like the red and the black cards in a deck. And once that's in place, it's easy to derive the complement rule, and you can see it can be expressed in 2 different ways. Easy. Wait till you see what's coming up next, though. Now, the multiplication rule is so complicated that it requires us to take a step back and introduce a handful of new ideas so that we can truly understand what the multiplication rule is telling us. The multiplication rule is defined in terms of what we will call conditional probabilities, which we don't know what they are just yet, but we will. And these in turns are computed from joint probabilities, which again, we haven't seen yet, but we will very soon. So in order to introduce these concepts properly, we're going to show you an example of what's called a joint probability table. And with this kind of table, each element in our data is defined in terms of 2 different categories. So you'll see what I mean when we get to the example. And these categories are, the way the table is structured, this will enable us to find the probabilities that we need, which are the so-called joint probabilities. And this one as well, which is now a new one, which is called either marginal or unconditional probability. So this all sounds very scary and intimidating, but once you see some examples, you'll realize that it really isn't. We just have to get an example going, which will make sense to everyone. Okay, so Now, here in this example, we're assuming that we're looking at a college, not Purchase, you'll see why in a second, that has a business school. Okay, Purchase does not have a business school. It has performing arts, but not business. Most schools that are not performing arts schools do have a business school. And in this school, you can learn different kinds of majors like um, accounting, finance, and marketing would be three standard majors that you would encounter in a business school. And also, most of them offer degrees at two different levels. BBA stands for Bachelor of Business Administration. That means you're getting a college degree, a traditional four-year college degree. But you may not have noted, but there's more school after college, although it is optional. You can go on in this field and get what's called an MBA, which stands for Master of Business Administration. That has to wait, though, until you're done with your college degree. Now, I think Purchase does have a few master's degrees. They're not MBAs. Some of the disciplines do have master's degrees. I seem to remember that last year, one of the students was applying to their master's degree program in opera. I never found out if he got in or not, but I'm pretty confident that they offer it. And so that means that's what comes after college. It gives you the opportunity to specialize further in the area that you're studying. I think for the other departments, they have something called MFA, which stands for Master of Fine Arts. But I don't know how that's done at Purchase. You could look it up if you were interested. Like, let's say you've decided, I love my major so much that I want to do more. You can stick around and maybe, or get a master's degree in that field, which gives you even more background in what you're doing. But for performing arts, it would typically be referred to as MFA or Master of Fine Arts rather than MBA, which is only for business. But anyway, you can see the students in the school, there's 500 of them. And they're broken up by the level of the degree that they're getting and what they're majoring in. So everybody in this table has two characteristics: the degree they're studying for and their major. Okay, so that's how this table is set up. Now, we're going to use letters going forward to represent these different events. For example, just to speed things up, so you don't have to write all the time, B will now represent pursuing a bachelor's degree in business administration, and M will, obviously enough, represent pursuing an MBA. Okay, now we also want to do the same thing with the majors, but we do run into one hiccup here. If you look at these letters, I can call finance F and I can call accounting A. I can't call marketing M because M is already taken over here with MBA. So here's what we'll do as a compromise. We'll let the letter T represent marketing. Okay, so don't be confused. T going forward will represent marketing. I could have picked any letter in there, but M. I could have called it K or N or G, but I chose the T. Okay, so this way, each of these letters represents a different event. B, again, for bachelor's degree, M for MBA, F for majoring in finance, A for majoring in accounting, and T for majoring in marketing. Now, we can introduce the first of our three new probabilities, the joint probability. We mentioned that earlier. These tables represent two kinds of probabilities: joint probabilities, and these other ones, marginal or unconditional probabilities. What are these all about? Well, we'll start with the joint probabilities. A joint probability is the probability that two events will both occur. And we've seen this represented before as the probability of A intersect B. And you might recall that this symbol for intersection is often replaced with the English word and because it means the same thing. So in other words, what I'm asking here, if I'm asking for the probability of A and B, what I'm actually saying is that I need to know the probability that both of them are true, not just one, but both. Like, for example, the probability that tomorrow it will be rainy and the temperature will be above 70. That's a joint probability because two different things must be true. One of them is not good enough. All right, now how do we calculate these in our table? Well, imagine the following situation. Now, this school, suppose they have an alumni magazine that's published every month, and every month, one of the business students is randomly chosen to be on the cover of this magazine. So you've got 500 students in the business school. All of them are equally likely to be chosen because it's done completely at random. What if I wanted to know that the person I chose for the cover is getting their bachelor's degree in finance? How would I figure that out? Good question. Okay, so let's look at our table again, and you'll notice something interesting. If you look at the intersection of the column, the row for bachelor's degree students and the column for finance majors, look at this. 130 students fall into both categories. They're both finance majors and they're getting their bachelor's degree. So therefore, 130 students fall into this category out of 500 for the entire business school. So this probability is actually 130 out of 500. So this is actually no different than what we did with the deck of cards. If I asked you, what is the probability of picking a spade out of a deck of cards? That would be 1/4 because 13 of the cards are spades out of 52 in the entire deck. So the same thing is going on here. We're assuming that all these people are equally likely to be chosen, just like the cards in the deck. And so therefore, this probability is 0.26 or 26%. And you notice how we've written this as the probability of B and F, meaning both of them are true. Now, just as a side note, I just want to mention that with these joint probabilities, they can be written in two equivalent ways. If you notice here, the order in which I write these events does not matter. B and F and B are the same thing. So don't worry about that. The order is not relevant. I just happen to pick the B first, but F and B would mean the same thing. Okay. So how about this next one? What if instead I want to know the probability that a randomly chosen student is getting their MBA in accounting? Ooh, well, based on the same logic, you can see that right here is where those two categories intersect each other. This column is all the accounting majors. This row is the MBA students. There are 35 who belong to both categories. 35 people getting their MBAs in accounting. And when you divide by the total population of students here, 500, you're going to get 0.07, which is 7%. All right, so here's your challenge. What is the probability that the person we've chosen is getting their bachelor's degree in marketing? How would you do that one? Well, I'll show you. Go to the table and look at the intersection between marketing majors and students getting a bachelor's degree. So that would be 90 out of 500, which is 18%. So in other words, we look at the intersection of the row containing all the bachelor students, the column containing the marketing majors, that intersection is 90. And so that probability, BNT, bachelor's and accounting, or marketing rather, equals 90 over 500, which is 18%. So you can see it's pretty straightforward. And once again, this probability is known as a joint probability because two different things have to be true. The level of the studying that they're doing and the major that they've chosen. All right, here's another one for you. Here's another challenge question. What is the probability that a randomly chosen student is getting their MBA in finance? Ooh, how would that work? What are we looking for? MBA in finance. All right. Well, what are we looking for? We're looking for all the MBA students in the second row who are also majoring in finance. And that means 45 out of a total of 500, which is 9%. So altogether, there are 6 joint probabilities that we could calculate. And I put them all together in one table here. If you want to go back and double check your results, you can confirm all of those with your calculator, and you'll see that there's 6 of them. And then, of course, all of them have to add up to 1. All these probabilities have to add up to 1. All right, now, what if here's another type of probability that's on this table. Oh, here we go. That's not true, no. Well, I mean, it depends on what you mean by that. In other words, each major is mutually exclusive of the other majors. And the level of the degree is independent. They're independent of each other. I'm sorry, they're mutually exclusive. But what's not mutually exclusive is the majors and the levels of the degrees. In other words, any major can go with any degree. So what's mutually exclusive is the individual majors. They're all independent, or sorry, mutually exclusive of each other. And then the level at which you're studying, those two are also mutually exclusive. You can't, for example, be majoring, or at least in this chart, I'll tell you what, you can't be getting simultaneously a bachelor's degree and a master's degree. In principle, though, you actually can get a double major, which means you can get 2 majors at once. But we're pretending here that that's not the case. We're pretending that at this school, you must choose one major and that's it. You can't get another major. You can't get a double major. You can't get a minor. Either you pick one major and that's it. Although in practice, it is possible to arrange a double major. If there's 2 subjects that you really care about and you're not sure which one to pick, you can do them both. Okay, I don't know if they discussed that with you when you got to the school, but it is possible to do that. Now, it takes longer, of course, but it is doable. You can get a joint bachelor's degree with 2 majors. Wow, does that start you thinking? And that includes math. You could double major with what you've got now plus math. That could be your second major. Ooh, and not only that, but you can actually have more than one minor. You can have 2 or 3 minors if you choose to do so. Oh man, you can really get ambitious. Imagine yourself double major, triple minor. It's doable. It can be done. And some places they'll actually allow you to design your own major or minor. You can put together a series of courses that make sense. and then choose to define your own major or minor. So, but here we're keeping it simple. We're assuming that you're either getting a bachelor's or master's, and then you pick one major, and that's all you're entitled to. And so therefore the columns are mutually exclusive of each other, as are the rows. Otherwise, these calculations would not be correct. All right, anyway, so now we're introducing marginal or unconditional probabilities. These are basically the totals. For example, what if I'm only interested in knowing if the student I picked at random is getting a bachelor's degree? I don't care about their major. I just want to know if they're getting a bachelor's degree or not. This is very different than what we've just been doing, because what I'm in effect doing is including everybody across this top row. The bachelor's degrees in finance, the bachelor's degree in accounting, and the bachelor's degree in marketing. It turns out they all add up to 400. And also, if you look carefully at the way I've written this, it's just the probability of B. There's no intersections here. So this type of probability is known as a marginal, or sometimes it's called an unconditional probability. Okay, so and you notice it comes from the total of this first row. So these in here, these are the joint probabilities in these columns, these rows and columns here, but these sums all are used to provide us with marginal or unconditional probabilities. So this probability, as you can see, is 80%. Now, what if I want to know that the probability that a randomly chosen student is majoring in accounting? What would I do? This time, I'm interested in the column sum. In other words, let's go ahead to this slide. I'm adding up all the accounting majors, whether it doesn't matter to me if they're getting a bachelor's or a master's degree. There's 215 total accounting majors out of a school of 500. That means the probability is 43%. And this is also an example of a marginal or unconditional probability. So you can see there's altogether 5 of these that we could calculate, these 3 and these 2. So here's your challenge. Why don't you tell me the probability that a randomly chosen student is getting an MBA? How would you approach that? All right, so here's what you would do. You would go to the row that represents the MBA students, and you would add them up, and you would get 100 out of 500, and therefore you end up with 20%. That's pretty much what you would have expected. 100 total MBA students out of a student body of 500 means the probability that you've chosen one of them is 20%. All right, how about this one? The probability that a student is majoring in marketing. What would you do this time? Oh, I know. Why don't we look at the column that contains all the marketing majors? So again, we don't care about whether they're getting a bachelor's or a master's. There's 110 people getting their marketing degrees out of 500, which means that that probability is 22%. Now, what you can do with these tables, by the way, in a case like this, if we don't really need to know the actual number of students in each of these categories, but just the probabilities, we can simplify this table a little bit by going through and dividing every cell by the total of 500. And that's going to give us all probabilities. So let me show you what that looks like. So I somehow managed to squeeze them both on the same slide. Here's the original table on the top. And down here, this is the result of taking every one of these numbers and dividing it by 500. And so again, if we only need to know the probabilities, this might be the better choice. But if you notice, if you're looking at this table down here, we don't know the actual number of students that belongs in each category. If we need that kind of information, the table on top is probably the way to go. But if we don't, if we're just interested in probabilities, we can create the second table where all of these numbers are already probabilities. And it might speed things up for us a little bit. Not that much, but it might be worth our while to do this. So you should be prepared to use either type of table to come up with these probabilities. All right, now, what this has all been building up to is this concept called the conditional probability. And why it's called that is because the probability of one event depends on whether or not another event takes place. Like, here's a simple example. Suppose that I need to know the probability that, let's say that a farmer's crops will be worth $1 million at the end of the year. Okay, when it comes time to sell the crops, we want to know the probability that they're worth $1 million. Most likely that depends on the state of the weather. So what we would probably have to say is the following. What is the probability that the crops are worth $1 million in the event that the weather is good? Because you can see that can change everything. So with conditional probabilities, we have two pieces of information that we need to know to come up with this probability. And the reason we saved this for last because this is definitely the most complicated of all the probabilities in this chapter. But we need them to actually implement our multiplication rule. So basically, all of this has just been a build-up so that you'll be prepared to understand what the multiplication rule is and how it's used. Now, this is where I left off with the other class. It's a very complicated idea. I don't want to start it and rush through it. So I think we'll stop right here. Just don't forget, I will post the sample midterm solutions along with the sample midterm, and then you can download everything, you can review, you can practice, and then send in your second midterm by, let's say, next Monday night at midnight, meaning Monday the 19th at midnight. That should be plenty of time to get everything done. All right, and I mean plenty. So anyway, in the meantime, I guess we'll stop right here and I'll see you all on Thursday. All right, any last minute questions? Okay, no.
Thank you. Have a good day.
Welcome. Okay, bye.